All right, guys. So apparently my first video did not record properly and couldn't upload it to YouTube. So here is my second try. Um, so we are finished with exponential and logarithmic functions, right? I'm sure you're happy to hear that. We only have two topics left. So we've got probability and statistics left. And probability is going to be a pretty short unit. And it's something I think you guys already know about. I'm not exactly sure where you learn probability, but it seems like most people have like at least like some kind of understanding of it before coming into Algebra 2. So I'm sure you guys can all do question number 1, right? But see if you remember anything else and try this first page up until number 7 as a warm-up. All right, so I'll give you a second to do that. Go ahead and pause the video. All right, so probability. If you roll a single die one time, what's the chance? So the probability of something is like the chance or the likelihood of that event occurring. So whenever you do an experiment, when you do something, right, there are trials. So in this case, like if you want to see what happens when you roll a die, the experiment will be rolling the die a bunch of times, right? And each trial, each time you roll the die, you get a certain outcome. The outcome is the result of your trial. So if I roll a die, what's the chance of getting a 4? Well, a die, if you do not know, is a 6-sided number cube, like so, right? It has 6 sides, and that would represent 1, that represents 2, that represents 4. I don't know exactly how the numbers are oriented, but right, that's a die. So the chance of getting a 4, well, one of the 6 sides of the die is 4. So that's a 1 out of 6 chance. And we are making an assumption here that every number has an equal likelihood of appearing, right? That's a pretty safe assumption, but we are making that assumption, right? If it's a weighted die, these numbers could be way off. So what's the chance that it's an even number? Where, well, there are 3 even numbers, 2, 4, and 6, right? So any of these outcomes are going to satisfy the condition of being an even number. So that is 3 out of 6. If you want to simplify, you can. You don't have to simplify for probability. You can leave it as 3 over 6. That's fine. All right, what's the chance of getting a number greater than 4? Well, the numbers greater than 4 on a die are 5 and 6. So the chance of getting a number greater than 4 is 2 out of 6, or 1/3. All right, what's the chance of rolling an 8? Well, there is no 8 on a standard die, so there is no chance of that, or 0 out of 6. There could be 0 out of anything, right? Because that is equal to 0, there is a 0 chance of that happening. It's an impossibility. Right? What's the chance that a number you roll is greater than 3 and an odd number, right? So when you see this word and, you have to satisfy both conditions. So we need to be greater than 3, so either 4, 5, and 6, and we have to be odd. So which number is greater than 3 or odd? Just this number, right? Just 5. So there is a 1 out of 6 chance to get a number greater than 3 that is odd. So pretty much there's a 1 out of 6 chance to roll a 5, because 5 is the only number that meets both criteria. But if I change that word and to or, well, now it's the probability of getting a number greater than 3 or an odd number. So 4, 5, and 6 are all numbers greater than 3, right? 1, 3, and 5 are all odd numbers. But there is an overlap in these two sets, right? They both share 5. So I can't count 5 2 times. So I'll make sure I only count it once. So the chance is 5 out of 6, right? Because I can roll a 1, 3, 4, 5, or 6, and that would satisfy one or the other criteria. So when it's or, you just have to do a number greater than 3 or an odd number, either or, right? When it's and, you have to satisfy both criteria, and you can see it makes quite a bit of difference. All right, number 2 says list the sample space. So the sample space is the set of all set of all possible outcomes. So when you roll a die one time, right, the outcomes are going to be 1, 2, 3, 4, 5, and 6. Right, but how about if you roll a die 2 times? Well, when you roll a die 2 times, you can roll a 1, right, and then another 1. You can roll a 1 and then a 2. You can roll a 1 and then a 3, a 1 and then a 4, a 1 and then a 5, a 1 and then a 6, a 2 and a 1, a 2 and a 2, etc. So I'm just going to copy this from my first initial take of this video. Right, or we can get a 2 and a 1, a 2 and a 2. We get roll a 4 and then a 6, a 4 and then a 4, a 6 and then a 1. Right, so we want to list out every single possible combination. So I ordered it so it's nice and logical, but there are all 36 combinations. Right, when you roll a die, the first time there are 6 possible outcomes. Right, first roll. There are 6 possible outcomes. When you roll it the second time, again, there are 6 possible outcomes. So if you want to know the number of possible outcomes in 2 rolls, what we're going to do is multiply the 6 and the 6, right? So another way you can represent all these possible outcomes and why it's 6 times 6 is if you list out all the possible outcomes for the first roll, and then we do branching paths, 4, 5, 6, right? After I roll a 1, I have 6 possible different outcomes. And same thing for the 2, 1, 2, 3, 4, 5, 6, same thing for the 3, right? So this we call like a tree diagram. This tree diagram is another way to represent the sample space. So you can see why it's going to be 6 times 6, because each of these 6 original outcomes has 6 additional possible outcomes on the second roll. So hence 6 times 6, we have 36 possibilities here. So 36 outcomes on 2 rolls. So what's the chance of rolling a 3 and then a 4 in that order? Well, if we take a look at our sample space, there it is. There's a 3 and then a 4. The chance of that happening, well, that happens 1 out of the 36 outcomes. And all these outcomes are equally likely, right? So that's a 1 out of 36 chance. 5 is a little different. It asks, what's the probability of rolling a 3 and a 4 in 2 rolls? So not specifically in that order. So rolling a 4 and then a 3 also is rolling a 3 and a 4, right? In those 2 rolls, I got both a 3 and a 4. So in this case, that is a 2 out of 36 chance. That is 1 out of 18. So the wording, as you can see, is kind of really important and it's kind of nuanced. So make sure you're reading carefully. And 6 and 7, we're going to come back to these. These are quite a bit more difficult, and you got to do like a little bit of a roundabout way of figuring out 6 and 7. So we'll go back to those in a second. But let's just talk about basic probability. So the probability of any event is going to be in between 0, which means it's impossible, and 1, which means it's guaranteed. That's 100%, right? All the probabilities we listed above, right? A 6, a half, a third, 5, 6, those are all found between the numbers 0 and 1 on the number line, right? You can convert them all to decimals and therefore to percentages if you wanted to. So when you add up all the possible outcomes, the probability has to be equal to 1, right? Because something has to happen. So when you roll a die, right, the chance of getting a 1 is 1 out of 6. The chance of getting a 2 is 1 out of 6. The chance of getting a 3 is 1 out of 6. A 4, 1 out of 6. A 5, 1 out of 6. A 6 is 1 out of 6. Right, when we add those all together, of course, we're going to get 6 out of 6, because that's 100%. One of these outcomes has to happen. So when you add up all the probabilities of the individual outcomes, it has to equal 100%, right? Because some outcome has to happen. So if all outcomes in the sample space are equally likely, then the probability that event A occurs can be found using this formula. Again, I'm just going to copy and paste to save a little bit of time. The probability of some event A is going to be equal to the number of possibilities that meet my conditions, whether it's I want an even number or an odd number or a number greater than 4, right? Those are the conditions I'm talking about, divided by the number of equally likely possibilities or outcomes. So if that's the chance that some event will occur, the chance that an event doesn't occur, well, let's say there's a 40% chance that something happens. Well, then there's obviously a 60% chance that it doesn't happen. So the chance that an event doesn't occur is going to be 1 minus the probability that the event does occur. All right? So if we call, let's say, some event A, and that A has some probability, right? So we can say the probability of not A happening is going to be 1 minus the probability of A happening. Right? If the probability of A happening, again, is 30%, the probability of not A happening is 70%. So there's different notation where we don't write the probability of not A. What we can write is A with this superscript C, like an exponent, but it's obviously not an exponent. It's just notation, which means complement of A. So complement of A just means the opposite. If you're thinking of sets, it means like everything not included in set A. So that's what it means. Just means not A, pretty much, essentially. So this is how we're going to write it, but that means exactly what we see above. So we can say the complement of A is equal to 1 minus the probability of A, the probability of the complement of A. All right. If two events have no outcomes in common, then the probability that one or the other occurs is going to be the sum of their individual probabilities. All right. What this means is, for example, what's the probability of rolling an odd number on a die? Or, let me write it out. So what's the chance of, what's the probability of rolling an odd number or 2, right? So these two events, rolling an odd number or 2, they have no outcomes in common, right? They do not share any outcomes. So that means if I want to find the probability of rolling an odd number or a 2, I can add those two probabilities together, right? The probability of odd plus the probability of 2. That's going to be, the probability of getting an odd number is 3 out of 6. The chance of rolling a 2 is 1 out of 6. So the chance of this combined is 4 out of 6, right? Compare that to when we did, which example? This example, a probability of a number greater than 3 or an odd number. So let me write that out. Compare that to the probability of rolling a number greater than 3 or an odd number. Well, we can't just add these two probabilities because the probability of a number greater than 3 and the probability of an odd number, right, there is overlap to those two outcomes because 5 is a number that's greater than 3 and 5 is also an odd number. So in this case, the two events do not have no outcomes in common. They do have outcomes in common, right? A 5 is an outcome that is common to both probabilities or to both events. So in this case, we can't just add the two probabilities. So hopefully that makes sense what Dad is trying to say there. And so now if we go back to number 6 and 7 here, based on those little bit of definitions and rules that we talked about, how can we find the probability of rolling at least 1 4 in 2 rolls? Well, I'm going to cheat first and just look at the sample space. And I'm just going to count all of the outcomes that have at least 1 4. So I'm just going to highlight all of them. And as you can see, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So there was an 11 out of 36 chance of rolling at least 1 4 in 2 rolls. All right. So we're not going to do this by drawing out the sample space every time and then counting, because that's going to take a long time. So try to think if there was another way you could have done 6, and also try to experiment with 7 if you want. I think they're good thinking questions. All right. But how can we figure this out? What's the probability of rolling at least 1 4 in 3 rolls? So in 3 rolls, we're going to have 6 times 6 times 6 possible outcomes, or what is that? 216? Why does that number feel weird? I don't know, it is 216, but just feels weird. All right, so we have 216 outcomes when we roll 3 times. So I don't think you want to write out the sample space for that, because you're going to be writing 216 different outcomes, right? You're going to be writing 1, 1, 1, 1, 1, 2, 1, 1, 3, 1, 1, 4, and that's a lot. And then you have to count all of them that have at least 1 4. So that is not going to be a good way to do it. So what most people try, well, they try by saying, at least 1 4. The chance of rolling a 4 is 1 out of 6. So people might try doing 1 over 6 times 1 over 6 times 1 over 6, but then you're finding the probability of rolling 4 3 times in a row, right? When you multiply the probabilities together, that's going to give you the probability of all the events happening consecutively. And obviously that is not going to be correct, because the chance should be a lot higher than that. So what we actually have to do is we have to find the probability of not rolling a 4, right? We're going to find the complement probability, because it's hard to find rolling at least 1 4. So what's the opposite of rolling at least 1 4? Well, could we find a probability of not rolling any 4s? So let's take a look. I'm going to set up a let statement. I'm going to say let this event A equal rolling at least 1 4, right? That's what we're trying to find, the probability of A, but we couldn't find that probability. So if that's a probability of rolling at least 1 4, then the complement of this would be not rolling at least 1 4. So if you don't roll at least 1 4, in other words, you're rolling no 4s or 0 4s in your 3 rolls. Right, so can we find a chance of rolling 0 4s? Well, yes we can, because what's the chance of not rolling a 4 on a single given roll? That will be 5 out of 6, right? We can roll a 1, 2, 3, 5, or 6, right? 5 possible outcomes that meet my criteria. So the chance of rolling not a 4 is 5 out of 6 on the first roll. On the second roll, the chance is also 5 out of 6. On the third roll, the chance is also 5 out of 6 again. So the chance of not rolling a 4 on 3 rolls is 125 over 216. All right? So we can multiply the probabilities together when one probability does not affect the other, when one outcome doesn't affect another outcome. And we'll talk a lot more about this later on. But that's also kind of what we did or that's another way we could have solved 4. Right? What's the chance of rolling a 3 and then a 4? Well, the chance of rolling a 3 is 1 out of 6 on the first roll, right? And then the chance of rolling a 4 on the second roll is also 1 out of 6. So that's 1 out of 36. So we'll talk more about when and when we can't multiply probabilities, but in this case we can do it. So that's the chance of not rolling a 4. So the chance of rolling a 4 or getting at least 1 4 is going to be 1 minus this probability, right? So the probability of rolling at least 1 4, the probability of A, is equal to 1 minus 125 over 216, which is equal to, I don't want to do this math. What is that? All right. Can't think. I'm just going to copy from last note. Right, it is 91. All right, that's 91 out of 216. right, so we could have done the same thing for 6 as well. We did not have to draw out the sample space. So what's the chance of not rolling a 4 in 2 rolls? That would be 5 over 6 times 5 over 6. Right, so the chance of not rolling a 4 is 25 over 36. And 1 minus 25 over 36 is 11 over 36. Well, so number 8 here, how do we know that this is a legitimate probability model? So the probability someone is never married is 0.506. And by the way, that is 50.6%, right? Just multiply by 100 to get as a percentage. Chance someone is married is 45.2%. So chance someone is widowed is 0.2%, less than 1%. And chance someone is divorced is 4%. So how do we know these percentages are legitimate or they might be legitimate? Well, if you add them all up, plus 0.452 plus 0.002 plus 0.04, well, they equal 1, right? So we know that the sum of all possible outcomes has to equal 1. So if these are all the different possible marital statuses, right, they should add up to 1, and I can't think of any other marital status you could have other than one of those 4, right? Maybe after you got divorced, you got remarried, and you want to make a separate category for that, but I don't know. So anyway, probability equals 1, so we know it's legitimate. So what's the probability that a woman is not married? Show 2 methods for arriving at this answer using the basic rules of probability. Well, we know the chance that they're married, I just used capital M, is 0.452. So the chance that they are not married is going to be 1 minus 0.452, right? And that should make sense. If you have a 45% chance of being married, you have a 55% chance of being not married. So this is 0.548 or 54.8%. The other method is we can just add up all of the other outcomes, that is not married, right? So if we do 0.506 plus 0.452 plus 0.002 plus 0.04, that will also equal that same number. All right, so usually in class, I do like a stations activity as an introduction to probability. So obviously we can't do that with remote learning. So I just posted the 6 stations below as a PDF file. So if you want, you can try all of those. You should be able to do all the questions now. I want you to complete that for homework. You don't need to submit it. I already posted the completed notes. So I did go through a whole bunch of questions on my original video. I don't really have time right now. So I'm just going to pick a couple of select questions and talk through them, right? I don't want to rewrite everything again. So which ones do I want to talk about? So H and I, those are really similar to 6 and 7 here. Same idea. So for H, if you spin spinner number 2 twice, this spinner, right? What is the probability of landing on an even number at least once? So again, you can't really find that probability directly. You have to find the probability of not landing on an even number at least once in 2 spins. In other words, what's the chance of getting no even numbers in 2 spins? So we have a 2 out of 5 chance of getting an even number. So therefore, we have a 3 out of 5 chance of not getting an even number. So the chance of not getting an even number is 9 over 25, and then you find the complement probability of that, which is 16 over 25. All right, and same thing for letter I. Number 2, what do I want to talk about here? So C and D, there's the difference between and or again. Right, for letter D, just notice the overlap. What's the probability of getting a red card or a jack? So there are 26 red cards, right? 26 red cards. So chance of getting a red card is 26 out of 52. there are also 4 jacks, or 4 out of 52, right? But you can't just add the probabilities, right? Because we said over here, you can only sum up the probabilities when, so I'm going to highlight this, when the 2 events have no outcomes in common, right? Then it makes sense to add them together. But if there is some overlap in their outcomes, like in this case, getting a red card or a jack, right? There is an overlap here because some of the jacks are red. So you can't just directly add, you also have to subtract the overlap here. So in 2 out of 52 cases, right, we're going to have some overlap. So that is how you can get 28 out of 52. Or again, you can just count up all the individual probabilities, which will be all of these guys here, and those, and that, and that, and that. And then if you count up all those boxes, right, we're going to have 52. Sorry, we're going to have, what was it, 28 different outcomes that meet our criteria. Right, and by the way, this is also another way to represent the sample space without having to write out every single thing, right? Kind of like a grid pattern. Paper place. Normally you would have an actual bag and you would count the actual number of pieces of paper. I just gave you the numbers I wanted you to use. So the thing I wanted to talk about here is the difference about when you put the paper back into the bag and then you pull out another one versus when you don't take, or when you don't put the paper back into the bag. So when you put it back into the bag, you need to know this vocabulary. That's called with replacement, right? That means you replace the piece of paper that you took out with the piece of paper that you took out. It just means you put the piece of paper back in, right? Without replacement means after you take the piece of paper out, you don't put it back in. So if there are 17 pieces of paper total, right, the chance of getting a blue on the first draw is 6 out of 17. And then if you put the blue piece of paper back in, well, there's going to be the same probability the second time. So that's 36 out of 289 in the two draws, right? Whereas if you don't put it back, it's a 6 out of 17 the first time, but after you take that piece of blue paper out, if you don't put it back in, now we only have 16 pieces of paper, right? And only 5 of them are going to be blue. So that's going to be a 5 out of 16 chance the second time, which of course is going to affect your probability. So just note the difference between the top and the bottom, whether you replace or don't replace the piece of paper that you took out the first time. Number 4, nothing too crazy here, right? The chance of getting tails 3 times is 1 over 2 to the third power, right? 1 over 2 times 1 over 2 times 1 over 2, right? We have a 50% chance each time. So getting it 3 times in a row is 50% times itself 3 times. What's the probability of getting tails on the 8th toss? So it doesn't matter what you got on tosses 1 through 7. If you got 7 tails in a row on the 8th toss, that doesn't affect anything, right? I mean, there's been like 1 million quarters that have been tossed in the past. It does not affect what you're going to be getting when you toss a quarter right now, right? So the past does not influence probability, at least not in this example, right? So this 8th toss is completely independent of what happened the prior 7 tosses. You could have gotten 7 heads. That does not mean you're due for tails. You could have gotten 7 tails in a row. That doesn't mean you're going to keep the streak alive and it's going to be an 8th tail, or that you're more likely not to get a head for some reason. So this one's kind of interesting. What's the chance of getting at least 2 tails? So the way I did this one is I drew out the sample space as a tree diagram, and I just counted a number of branches or paths that have 2 tails as an outcome. So in this case, right, that's heads, tails, tails. This is tails, heads, tails. I could have gotten tails, tails, heads, or tails, 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 right? So out of the 8 possible outcomes, 4 of them have at least 2 tails. You can also do this with a calculation if you are clever enough, but I think this is the easiest way. Just a tree diagram here. And right, tree diagram here for number 5 as well. Here is the sample space written out. And I'm sure you can do this two-way table. All right, just fill in the numbers. Over here, down here, when it says probability that a sophomore chose red, that's going to be out of the number of sophomores, not out of this total. Right? So the probability that a sophomore chose red, well, 50 out of the 166 sophomores chose red. So that's the probability that a sophomore chose red. If I wanted 50 out of 511, I would have said, what's the probability of sophomore and red? That would be 50 out of the total 511. All right, so I know it's a very fine difference. We'll talk a lot more about this when we actually do this topic. Right, there's a topic that is completely dedicated to the difference between these kinds of wordings. So this one is saying the probability that a sophomore, so out of the group of sophomores, what's the chance that a sophomore would choose red? And this is saying out of everyone surveyed, what's the probability that they were a sophomore and chose red? Right, if that's confusing, we will be talking about that a lot more later on. So that's going to be it. That is my re-recording of this video. If you have any questions, let me know. Finish up all of these stations if you haven't already. So hopefully you check. Let me know if you have any questions. And as always, stay safe and take care, guys. I hope this video will save properly. All right, let's go.